Yeah, thank you. So let me share up my screen and try to get the presentation up. I'm going to need everyone to sort of, host disabled attendee screen sharing. Is that a thing that we can toggle?
Try again, Frank.
Perfect. All right. Sharing this desktop, and now we're doing a play thingy. Can folks see this largely clearly? Actually, sorry, I need to minimize some of the controls first.
Ooh,
does this look good for people?
Yeah, looks great.
Perfect. So yeah, I'm Frank Sherry. I'm chief scientist at Materialize, which is mostly a title chosen to make sure that I didn't take any other responsibilities on that should actually be managed by professionals. And I'm going to be telling you about Materialize. This is both the name of the company, but it's also there's a software stack that builds on a few cool pieces of technology and has some opinions that are going to dovetail with some academic research, but also have slightly different take on some parts of technology, and maybe have some thoughts about what's good to work on next. We'll see. The talk is meant to be understandable, so if you have any questions, definitely interrupt and ask. I can't really see any of you, so if you have confused looking faces or something like that, you'll definitely need to stop and shout. Yeah, feel free to ask as we go along. I'll try to clean up sort of cleanly at 4:30. Hopefully I don't screw that up, and I'll make sure that you're definitely allowed to go at that point. And if I left anything delicious behind, I'll either save that for afterwards or share out the slides. Cool. So I'm just going to start with a little bit of background, just to get folks on the same page if you're not already. This is a traditional relational database, online transaction processor. It's a soothing shade of blue here. It does a bunch of things that databases are traditionally designed to do to serve as a source of truth for your data. So it accepts read requests, write requests, transactions, or lets you look at your data, put stuff in there, read stuff back out. Now, it's also capable of supporting a bunch of other analytic tasks. So people come and might ask complicated questions about it. They might repeatedly hammer it with questions to drive dashboards that are meant to reflect the current state of affairs, or other task monitoring as an example up there. But there's really a lot of stuff you could use this database for. They're pretty popular, turns out. Now, this causes the database to heat up. Basically, it's doing a lot of stuff that it wasn't exactly designed to do. It's not what it's best at necessarily. Pretty useful thing, but it gets hot because it's pretty popular. And that got fixed basically, or people realized, well, these tasks that you need to do, we could build a different thing. So in this case, an OLAP database is something designed for analytic processing, designed differently though, right? So instead of a row-based system for your transaction processor, you might pivot your data around into columns. That makes it easier for the analytic processor to grind over the data faster and serve all of these analytic requests much more efficiently. So that was popular. You've probably been around for that and seen some of these, but fundamentally nothing essential changed. Like some constant factors. I think this is 10 times more efficient, let's say, or more. But people are still just asking lots of questions. You make it a little bit more efficient, people are just going to ask more questions. They're going to refresh their dashboards more often, put more data in it. So these systems are still quite hot at the moment. If you go and you look at a data warehousing application, people are still hitting more queries than they can tolerate. They're not coming back as quickly as you'd like. So what we're going to talk about here is another attempt to fix this in a different way. So again, we're going to think about a separate design here, where we don't build a transaction processor, we don't build an analytic processor either. We're going to build, and this abbreviation is not meant to stick, but online view maintenance, basically. If we think of the task, not of answering arbitrary ad hoc questions, but of keeping your queries up to date as fast as possible and build a system for this. We can build a system now in a different way than the previous ones. And the fundamental pivot that we're going to do here is switching from pull-based architectures, where you show up and surprise the system by asking a question that it couldn't possibly have anticipated, to a push-based system, where you essentially announce ahead of time, these are the sorts of things I'm interested in. And you let the system manage that computation for you as the data change. And in the limit, this does something exciting, which is it removes how often you want to look at the data from the performance consideration. So really, it becomes more about how much does the data change, rather than do you want to refresh your dashboard once every second, every millisecond? Are there 1,000 people asking the same question? Those things shouldn't matter if we do our jobs well. So that's sort of the positioning, I guess, of what we're trying to do. Is a data processor looks and feels like the transaction processor, except that it's optimized for a particular use case. And naturally, Materialize is the instance of this thing. I'm not as aware of other examples of this out there in the wild, so I don't have good analogies for what's another instance of this that you should look at. Though having said that out loud, I'm probably gonna be wrong 5 times over, and y'all can correct me. But so that's the setup. I'm going to walk you through a little bit of the layers of the stack here, and then try to introduce you to some of the new parts and tell you what's complicated or not as easy as you might have hoped. So Materialize, right, is meant to present as a SQL interface and incremental view maintenance sort of interface where you present standard SQL queries to it. SQL 92 is what we've chosen to do for people who are excited about where does that come down. And our task is going to be to keep you as up to date as possible on the queries that you've expressed as your data change. The stack here is built on top of Differential Dataflow. You might be familiar with that. You might not. I talked about it in the Rise group, I don't know, 3 years ago, maybe? I can't recall exactly, but a little while ago. Which we'll talk a little bit about. It's essentially a framework for doing low latency data parallel computation. So the sort of big data computations you might write in something like Spark does those things, except allows you to arbitrarily change the inputs and get low latency updates to the outputs. And this is all built on top of this timely data flow layer, which I think of, don't read too much into this, but I think of as a bit of an operating system for streaming data parallel compute. And I'll try to back that up, but basically it provides a bunch of primitives, relatively agnostic to their uses for communication and scheduling and stuff like that. To give another take on this, here's the same sort of program written in each of these different frameworks. So Materialize is meant to be a thing where you show up and you just type some SQL because you like typing SQL and you don't like thinking about how computer systems work under the covers. This is doing some 3-way join and then some aggregation after it. You could also write this in Differential Dataflow, which is a bit more of this fluent programming style where you trick people who are used to writing imperative code into accidentally writing declarative computations by telling them that these are objects that have member methods, and you could take a collection and call join on it, and there's some people like, I know what that means. That's great. That has a method called join and it produces an output. You're like, yeah, it's definitely the collection that is a result of those 2 joins. You're holding it in your hands. And the big trick is, of course, it doesn't actually do that. It just builds up a query or a data flow graph in the background. But this is now, unlike up above, which was SQL, this is now, in this case, Rust code. So if you want to use this layer, you need to be a bit more familiar with Rust. You need to write a compiled program that might take minutes to build, for example, whereas the SQL above is meant to execute immediately. And that's all layered on top of timely data flow, which is this actual data flow execution environment where you assemble data flows more or less manually. And the meaning of the data flows you get to assign, you get to supply the implementation of each of these operators. I've written join and reduce and stuff like that, but you have to actually write that code yourself. And that can be easy or hard depending on what you're doing. And the intent, and this is sort of visually drawn in the stack over on the left-hand side, the intent is that Differential Dataflow builds on top of timely Dataflow, but does not conceal the surface. And Materialize can tap into each of these levels as appropriate, or indeed, anything else you'd like to build on top of the 2. But Materialize is the subject of the talk here. All right, I'm going to say a little bit about first timely data flow, and I'm going to try to call out some important moments in it that there's a lot of exotic stuff going on, but there's a few things to call out. And then the same with differential data flow before barging into what's going to Materialize. So working our way back up, timely data flow, like I said, I like to think of it as a bit of an operating system. It's not nearly as complicated as a real operating system, but it does provide abstractions for execution for cooperatively scheduled fibers, which are these operators in the data flow graph. Provides abstractions for communication, is moving the data between the different operators. Coordination, and this is a thing that's, I would say, fairly common in time-aware data flow systems, which is that the messages that get communicated around the data flow have a time branded on them. And each of the operators are allowed to or learn about the timestamps that they might still see on any of their inputs. And an important part of, I just want to call this out now, an important part of data flow systems is that a lot of the coordination is more passive than in other forms of concurrent programming. So like rather than, you might have a mutex in a different system and you manually, like you grab the mutex and you prevent anyone else from doing a thing. It's very different in data flow systems where you can't force any computation to happen. So you just sort of learn about what's going on in the world around you. And potentially once you've learned enough, you've learned that you won't see any more messages with a particular type, then, with a particular timestamp, then you can go and make your own progress, but no one else can sort of force you to execute at that point. You can't force other people to stop. So I saw there was some sort of question or comment in the chat, but I can't actually select it because of the Zoom interface. If it's crucial, yell it out and we can answer it. But otherwise,
I was just talking about how nice your slides are. Please don't worry about the chat people. If they have questions. I was just saying, wow, these slides are really nice. Don't worry about it. Sorry for distracting.
No, that's great. Actually, I mean, if you want to say that sort of thing every few slides, I'm super happy with that.
Just imagine me saying it. Okay.
So the fourth thing that goes on is scheduling. And this is actually one of the big departures from a lot of the other big data systems you might be familiar with. We actually handle in our worker threads the scheduling, cooperative scheduling of all of these data flow operators, instead of just relying on the operating system to assign each of them to a thread and let the operating system figure it out. We actually walk through each of these data flow graphs to make sure everyone gets scheduled certain amounts of time. And there's some nice things about that. So let me call out some of these properties. One is that since we're handling our own scheduling, we can multiplex millions of operators. Basically, we can decouple the complexity of the data flow graph from the compute resources that we have. So we might just have a single worker thread. It's totally fine. You can run arbitrarily complicated data flow graphs. You could have 32 workers and just a data flow graph with 3 elements in it. That's fine. We will partition all the work out across all of those workers. And in fact, I guess the thing to call out is each of these operators are actually sharded over all of the workers. So we've drawn, there are 8 plates basically going back for each of the workers here. All of the workers have the exact same data flow graph. So if you think of the data flow graph as the program description, right? It's like sort of like the binary you'd use for running a thing. It's a map of where the data need to go. All of the workers will have the same data flow graph, the same map. They just have different data. And it's the movement of data that's actually going to drive computation. So if you want join to execute only on worker 0, everyone should send all of their data to worker 0, but everyone still has the same map, the same data flow graph. By default, actually, everything will be sharded as much as possible. Yeah, sorry, go ahead.
So when you say everything, can you scope that first? Is that all live queries in the system are all one giant data flow graph, or is this scoped to a single query?
So that's a good question. The way it works in timely data flow is that you can have as many data flow graphs as you'd like. Each data flow graph, once constructed, its structure is static. The data can change and move around, but the graph stays static. The way it works at the moment, at least, is that of your set of workers, which are statically set up when you turn on the system, all data flow graphs are sharded across all of the workers. So if you have one really heavy, busy data flow graph and one really teensy-tiny data flow graph, they'll both be scheduled across the same sets of workers. They'll interfere, which is potentially bad, but also potentially good, as I'll try to get to in a slide or two. I don't know if that I think probably technically answers the question, but may have missed sort of the essence.
No.
Oh, good.
That was everything. It's sometimes people
Cool.
Sort of build graphs of graphs and then call that a data flow graph, and sometimes people talk about it the way you're talking about it. So I just wanted to.
I'm sorry. Yep. I've definitely not been sorry. This is definitely not enough information for someone to go and faithfully represent all of timely data flow words. So feel free to approximate as appropriate in your mind. We'll call back to some of these points in just a moment, and hopefully nothing will have been misleading. We'll see. The other point to call out, and this might sound a little esoteric, but it turns out to be pretty important, is that the timestamps can be partially ordered. Most of the time, people think of timestamps as being integers. Like, goes up, it counts, I don't know, number of milliseconds since 1970 or something like that. This is able to be substantially more general in a way that's going to be pretty empowering. I'm not going to say too much about why this, I mean, it's a really cool thing to talk about. We'll see how we get to it. One of the things we try to do in Materialize is hide a bunch of complexity. So our goal is really actually not to show this off too much, but there's some neat connections if you're in the streaming space to event time and system time, and how to reconcile those two things that we can deal with in a really slick way that other systems kind of struggle with. Mm-hmm. So let me barge ahead. Sorry, if folks, this is a great time to ask questions about timely data flows. This is sort of the summary for it here. I think the level of abstraction that we need to go forward, but I'll briefly pause.
You did say an intriguing thing about pushing and pulling before. I don't know if you want to get into that in any detail.
Yeah, okay, that's a good point. I mean, so data flow graphs don't force you into a particular computational model. You can use data flow graphs for both push and pull. The execution model here will absolutely be push driven, though, in the sense that the scheduling happens as a result of a few things, one of which is the arrival of data. And the movement of data is really going to be what prompts scheduling. So in a data flow graph like we have above, the join operator, first one, isn't going to do any work really until input 1 or input 2 provides some information to it. It's going to be idle, and it's going to essentially be zero overhead for the system. We're not repeatedly going to ask it, hey, do you have anything to do? We will only chase down work that needs to be done as a result of actual data moving into the system and then through the data flow graphs. So this is part of what lets us, like this millions of operators thing, for example, is actually one of the examples we have for Timely, which has 1,000 data flow graphs, each with 1,000, like essentially a path 1,000 elements long. And the question is, can we repeatedly schedule and move data through here without eating an additional factor of 1,000 that would show up if we were a little sloppier? Yeah, I think that's all that I can think to say about it. Yeah, we'll see if that's a bad idea, but let me barge ahead. It's basically, we're moving up the stack a little bit, and the thing that happens as we go from timely data flow to differential data flow is we get some more opinions about what things should mean. So timely data flow didn't really care what the operators were, it didn't really care what the data you were sending around was. It provides some properties about coordination and I don't want to say synchronization, but scheduling, stuff like that. Now we're going to introduce some opinions. So differential data flow is going to try to play the role of incremental view maintenance for data parallel computation. So you write a program, think of it, if I say Spark because I imagine there's a lot of familiarity with that there, but think of your favorite data parallel programming language, SQL, maybe Spark, something that you would use writing against a static data set. And our job is to both execute it against that static data set, but then also to keep things current as the underlying data change. So we're going to allow you to change the underlying data, and we're going to attempt to update your computation for you in as little time as possible. Now, the streams here, which were previously just random data that had timestamps attached to them, are going to be a bit more specific. They're going to represent CDC. CDC is change data capture in the database world. I understand that that's not the most popular use of CDC at the moment, but this is what people think of this as. Think of this as the exhaust coming out of your relational database as you insert into and potentially delete from that database. And in particular, we're going to model this as some triples. Triples of data time diff, just that's how differential data flow does things. Let me spell out what each of these things are. So data, this is describing a change that happened to a collection of data. The data field is like the actual payload, the record. If this were a relational database, this would be a row in the database that might have been added or removed, something like that. Though it doesn't have to be relational. It could be, JSON blob or some weird stuff like that. But it's some relatively opaque payload. We need to be able to equate them to one another, but that's about it. Time is a logical time at which this change was meant to have happened. Everything in the system in differential data flow is going to be based on logical times. They will happen at real physical times, of course, like everything does, but we're going to be modeling the computation as a transcript of changes to a collection that happen at specific logical times. So you can think of this as either a timestamp that someone has branded onto the data at the input, or maybe as a transaction ID, for example, if this is coming out of a relational database, but it's something that says what things happen at the same time, what things happen at different times, which of them might come before others.
how are we supposed to imagine a logical time being structured? Is it going to be like an epoch number and an iteration number and a sub-iteration number in some contexts? Is it going to be nested? Is it going to have structure? Is it just some scalar that somebody knows how to interpret?
That's a good question. The easiest thing to think of it as for most of this talk is as an integer. Like that's sort of the easy way. If you're already feeling challenged by any of this, just an integer, great, time goes along. We're not going to do anything wildly exotic with it. In differential Dataflow itself,
you did tell us to pay attention to partial orders, though. So I'm trying to.
It's great. You're absolutely no. That's perfect. In differential Dataflow itself, so Rust has some nice generic programming support, and the only thing that the time generic parameter has to satisfy is that it's a lattice.
Yeah. Okay.
So the actual structure, we don't care. Like the compiler will find out when we try to compile the code. You just need to support certain mathematical properties, essentially.
So we should think of vector clocks, though.
You can if you want. You don't have to. And there's several non-vector clock things. Like most of the actual applications that I'm familiar with aren't actually vector clocks. People really leap to them really quickly because like, that's what I know of.
Well, I'm also imagining like nested structures. Like if I'm doing timely data flow, I might have a bunch of like sub iterations that I'm trying to track, and I might be doing a machine learning job. And at the level where I'm actually doing the differentiation, which is what I imagine is happening next, I might actually care about doing it at that granularity. You know, I want the kth iteration of the jth epoch of some, I don't know.
That absolutely makes sense. And maybe actually, if you, by the end of the slide, the times will make a little bit more sense, or the times are going to tell us essentially along what surface should we try to do differentiation? What should we try to take things as differences from each other? So like in principle, the times could be all incomparable, unrelated. And that sort of corresponds to batch processing, where you say like, don't try to do a diff off of anything. These times have no relationship to one another.
Sure.
And as you introduce more structure to the times, you're having a stronger opinion about when we do our differencing, what is it a difference from? What came just before this thing?
Yeah, that makes sense. Thank you.
Cool. And sorry, the diff, I advanced already, but diff is easiest to think about as an integer. This is the change to the multiplicity of a record. So if we're thinking of these as multi-sets, like there's a data, it occurs some number of times, some number of occurrences, I guess. I don't want to say time too many times. And the diff tells us how did that change? We have a +1, we got a -1, that would correspond to the addition of a record or the subtraction of a record. And at any point in time, we can reform a collection by adding up all of these updates with a time field less or equal to the query time and add up all of the diffs. If anything adds up to 0, we throw it away. Otherwise, the accumulated diff is the multiplicity in the collection. All right, there's a bunch of standard data parallel operators that have sort of natural implementation. So if you think map, filter, reduce, join, a few others. If we live by this sort of guiding principle, that each of these operators must have the property that the output it produces, it describes a changing collection, and that collection at every time should always be equal to the accumulation of the input at the same time with the function applied to it. So essentially, these things need to correctly map across times where we are going to accumulate the input and differentiate the output. So they're sort of correct if we connect up chains of these things on streams of diffs. They perform the correct logic there, is the requirement.
Hey, Frank. So I'm seeing here that you have the 3-vector or the 3-tuple. Time here is serving like a consistency, like transactional role. The diff is just, it's an optimization, right?
It's a bit more than that, actually. It's a thing that it's doing is it's making our update format into a associative commutative group. So especially when we have partially ordered times, it can be a little tricky to figure out how did a thing change. And the diff is something that allows us to say, no matter what your collections were, we can always figure out, we can always produce a diff that corresponds to a change from one collection to another. And in some cases, it it gets more complicated with the multidimensional stuff. This works out really nicely. There's some other encodings you could use. So people like to occasionally use these upsert encodings where you have a key, for example, and the most recently seen data associated with the key is the data. And that doesn't work out perfectly for a few reasons, mostly related to partial orderedness of time. But yeah, I don't think of it as, I might be wrong, I don't think of it as optimization so much as like it's an important, like it's not the most magnificent of the 3 elements in that tuple, but I don't know a good way to get around having it.
I think your comment about commutativity and associativity is really interesting. And then I think you're talking about the uniqueness, which is, I don't know, item potency. Is that not something, is that not a property that's necessary in differential data flow?
It is not necessary. It's something we end up, well, yeah, no, if you, sorry, it's definitely not idempotent. And if you took a tuple and you repeated it, which can definitely happen, you should take the cumulative effect of those 2 things. Like if you add a record twice at the same time, the count should be 2, or should increase by 2.
Thank you.
So I have a question. So Frank.
Yeah.
So is like for the implementation of these data parallel operators, is it like the responsibility of the developer to ensure that they have these kind of properties that you're mentioning, or like does your compiler somehow check that?
It's my responsibility. It's my job to have implemented these correctly. So all of these are parametric in closures that describe. So the map is not something that a user writes. A user gets to write the closure that goes into a map that specifies the so a functional relationship between input and output.
I see.
And so I've sweated and sort of bled into the implementation in a way that hopefully no one ever has to do again.
I see. Cool. Thanks.
Yep. Let me call out a few things and just sort of move along. I just want to get to the sort of the key takeaways from these things. In addition to these sort of more traditional operators, there's a few non-traditional ones. One of them is exciting. I don't want to say too much about it, even though it's super exciting. Iteration is a thing that you can do in differential data flow. That's sort of surprising if you're familiar with data log. It's a little hard to incrementally update a lot of recursive computations. It works out okay because of these multidimensional timestamps. The more relevant thing here, though, that I like to call out, and the sort of the more new thing, is an arrange operator, which, if you're familiar with databases, is a bit like an index build operator. It says it's a logical no-op on the stream, but it changes the physical representation to be a not just a stream of these changes going on, but a pair of a multi-version index over the contents of that change stream. And again, also the stream, though its shape will change in the output, it has a bit more structure. So what this does is it allows us to have both a change-based view of the data through the stream and random access to essentially to historical data on a key basis. Yeah, and this you might say, why do you want this operator? You know, what is it used for? And it does a few interesting things. So a few of them, for example, like it allows you to replay streams. So a lot of streaming computation, the first presumption that people make is, well, clearly you're not going to keep history around. So like clearly I shouldn't ever expect to have the correct answer on historical data up to this point, because you must have thrown some of it away. So they ask you to window your computations, for example. And this is super frustrating to people who have, for example, a database of customers. Like, no, my customers didn't vanish yesterday. Like they're still here. And in fact, I'd like to keep my customer data collection unwindowed, please. I might happen to window recent events, for example, recent purchases, but please don't delete my customers or their contact information or anything like that. So it allows you to maintain full historical detail about these streams and introduce them into computations. You know, you get to eat the memory requirements associated with that. So if it turns out it's too big, that's too bad. There's no magic here about that. But you aren't obliged to delete lots of data. Also, and sort of relevant in the relational setting, is much like an index in a relational database, you can share these arrangements, the multi-version index, between Dataflow operators. So in the picture up above, let's imagine that input 2 and input 3 were the same pile of data. Like you're joining against your customer data set twice using customer ID. They can both use the exact same in-memory data asset, which is really handy from the point of view of making these queries deploy quickly and not require a lot of memory while they're running, especially in relational settings, because a lot of these collections are the same and are indexed by keys that are sort of shared across many queries. Like when you access your customer relation, you often have a primary key. You often are joining on something being equal to that primary key. You want the data arranged the same way as everyone else has been using it. I won't say too much, but the main verb on this operator, or this index data, I guess, is supports compaction, logical compaction. So you're allowed to say, I don't care about historical distinctions between two historical times. That allows us to maintain a footprint that's proportional to the sort of the current size of the accumulated collection. All right, so I'm going to drift up one level. Arrangements are the main thing that we're taking out of differential data flow, or the main thing that's going to find a lot of purchase in this relational setting. Oh, I have some cute little, this is where Peter pops in and says how nice these look. Arrangements are very important, and because they allow replay, if you happen to have two arranged collections, you can just drop in after the fact and start a new data flow that starts from correct answers and starts to show you differences flowing forward. There's a paper to check out if you're interested. We have a paper on this in BLDB 2020. If you search for either shared arrangements or just my name, it's the only paper I have there, so you can totally find it there. And this is a much more traditional academic take on things if you are into that type of thing. I'm not as much anymore, but. All right, so that was differential data flow in a nutshell, and absolutely not doing justice to all the exciting things that you might have wanted to know, but we can pick up on those off of the critical path. So I'm going to tell you a little bit about Materialize and sort of sketch what the moving parts are and what's hard in it, or what's non-trivial, let's say. So here's an architectural diagram for Materialize. There's 3 layers that I've drawn here. I put the stuff that's important to me at the top, but that's not entirely fair. There are a bunch of clients that connect to Materialize. These folks are speaking SQL, basically. Actually, they're speaking PGWire. This is sort of standard protocol that a lot of people use, Postgres wire format. SQL, I say actually because it's a very common practice in the big data space to implement SQL asterisk, where the asterisk says like, lol, but not actually, we don't do the hard stuff. So we're actually doing the hard stuff. We're doing, correlated subqueries and like all of the surprising esoteric semantic properties of certain parts of SQL that are like surprisingly frustrating to get correct. But the take is that there's a bit of an uncanny valley between actual SQL that works as it's expected to and maybe kind of sort of SQL, and that if people can't rely on it being correct, it's not nearly as valuable. That's an industry take on things rather than academic take, but yeah. It gets turned into an intermediate representation, sort of maintained in the same way that a database might worry about these things. There's a catalog mapping names to intermediate structures. I'll explain a few of them. And ultimately, when needed, things get rendered down to data flow in this data plane that lives behind this front end. So the clients aren't actually talking to the data flow layer. That sort of access that is carefully managed so that it can move along as quickly as possible. It pulls in data from, let's say, a change data capture from a relational database, spits it out to some Kafka, or it can pull it in and out from various places. Like it can integrate a bunch of these things together. That's sort of one of the exciting things is that you can mash up your Kafka data with your relational database and line up the consistency boundaries in the two. If we look a little bit deeper, the main thing is going here. You've seen the timely data flow picture before, but just to sort of spell out what these things are, you not uncommonly put together little bits of SQL that say, hey, I've got a view in mind. I'd like to define something called orders from some source. That's almost certainly going to land in an arrangement. Idiomatically in Materialize, we think of them as indexes because that's what the SQL users have been trained to think of them as, but mechanically it's a differential data flow arrangement. And as you build up a few of these, you might create some views, name some things. I'll show some examples in just a moment. Build some more complicated things. So here, we just joined a few things together, reduced them, got into sales. And because differential data flow has all these nice logical timestamps in there, sales is going to reflect a consistent view, or it's going to reflect the same consistency as presented in orders and customers. If those are nice and consistent with each other, sales will only show consistent, correct views there. Yeah, you repeat this a few times, and because arrangements are nice and magical, if you want to use sales again, we already have that arrangement sitting around. We'll just literally reuse the same in-memory object, even across data flows. It's totally fine. And give you, it's always good to end on profits, because that gets people excited about things. But yeah, we're just, like, our job is mostly putting together these data flows for you, trying to reuse as much as possible the existing assets, because memory use is the thing that kills Materialize. This is the main trade-off we're making, is that you're willing to spend a bit of memory to make querying a bit faster. And if we can make that cost lower, then people are a lot happier. And if we screw it up, you don't have enough memory and you can't do the thing. All right. I'm just going to show a few quick examples of what these fragments look like. Stop me at any point if things are not making sense. But like, really, the intended look and feel is as unsurprising as possible, which, without getting too contentious here, like making it be as simple as possible is our goal. We don't want to invent any new things. We want to make things look exactly like people have experienced them before. Even if we really wish that they would do things differently. It's a different take in industry. So just looking down, actually, sorry, looking down the left side. Oh, someone had a question. I wanted to swing back at that. Go for it.
Could we move back to the previous slide for a second?
Sure.
So this
I can
particular
repopulate it.
example, if you could skip through the animations real quick. That'd be awesome.
I have no idea how to skip through the animation, so we're just going to watch all of
the
them.
profits.
Yes. Okay. So in this particular example, this is actually a pretty straightforward example where you know that you are possibly reusing the view on sales, right? So this Materialize view, you're planning on reusing it to compute profits. I guess you could make this sort of arbitrarily complicated, right? You could recognize that some portion of a data flow that you computed in the past could be reused for computing something in the future. And in general, I mean, we know that there's been a ton of work on sort of like view-based rewriting, right? So, and sort of how do you efficiently make use of stuff that you've computed in the past to compute new stuff? How much are you pushing on that direction, or are you just simply saying, if you've computed something in the past, I'm not going to compute it again? We're not really trying to fully solve the, I don't know, view rewriting problem. So how much of that sort of, but I guess the question is, I mean, there's a lot to be gained from doing that. It's just a very complicated question.
So I think the answer is that at the moment, we're not pushing on that at all. We're,
okay.
One of the things that we're very careful of at the moment, at least, is making sure that there's a clear contract between what the user types and what we do. So we want to only make certain operations actually cost memory, for example, because understandability is an important thing for us, which isn't to say that multi-query optimization or anything results in not understandable views, but we want to keep things as simple as possible to start. You're absolutely right that we have a lot of opportunity for doing that sort of thing, and it's made even better by the fact that all of the computations that we're dealing with are deterministic. So transaction processing is somewhere else, so we can totally spin up a second plan. We could rewrite these two, for example, into one common data flow, spin that up concurrently, and switch over to it relatively seamlessly in a future version of Materialize. It's definitely not happening at the moment, but there's a lot of potential for value to show up in rewriting and managing the current set of data flows. One of the things I'll get to in just a moment is that one of the challenges is query optimization, which is different now than it was before. A lot of things have changed. Queries aren't one-off. They need to be planned to run over time and to be memory sensitive, stuff like that. But you're absolutely right that there's a lot of potential for good stuff. It's not a direction that we're leaning on at the moment.
Thank you.
All right. So just sort of flip through this. This is really just meant to show off the life cycle of maybe someone working with Materialize. You create some sources of data. The sources are not actually data. They're just descriptions of where you could find data if you were to go and look. So usually this is a file, this is a Kafka topic, stuff like that. Nothing actually happens in terms of computation yet. We're just naming where to go and find things. Fortunately, SQL users have been trained with the concept of views. Views are great for us because they tell us essentially a quantum of what a person might be interested in maintaining. Right? So in this case, this is, by the way, the example is TPCH. It's not super fascinating, but I just copied and pasted literal Materialize code that we're using. So we're using views and the idiom of views to try to elicit from the users what are the natural boundaries in their queries where we could potentially materialize things. We don't have to. And in particular, if you just create a view, we don't actually materialize that yet because you haven't actually expressed an interest in having it materialized. But it gives us some structure that we can start to work from. The index is the thing that corresponds to an arrangement. This is where we actually go and build a data flow and start maintaining computation. So loading up data, sitting on it, seeing what happens, that sort of stuff. And the intent here is that this is absolutely an operation where people understand that building indexes is potentially expensive. So it's not super surprising, we hope, that when you build an index, we might go and start to squat on some memory. And in this case, I've just built indexes on the primary keys and foreign keys in line item. And with those in hand, I mean, you don't have to build those, but with those in hand, you can start to create other views. Here I've created a materialized view. This is a view that is essentially we're asking it to be indexed. At the end, it builds the data flow and makes this view immediately selectable with low latencies. And it's a 6-way join. It's a 6-way join that if the input data are brought in with the appropriate consistency in their timestamps, will only show you consistent views of the 6-way join. Even as the various bits of data stream in, it's smart enough to figure out how to make sure that it only shows you correct results. And it's going to take advantage of those indexes we just defined. So we just defined a bunch of indexes previously on line items with a bunch of foreign keys. And we'll have similarly a bunch of sort of primary and occasional foreign key indexes on things like customer and orders and whatnot like that. And we can set them up in a way that this query can deploy more or less immediately and start turning back answers, because it doesn't need to build up, if all the indexes already exist, it doesn't need to restream any of the data and reform any of the indexes. They're all sort of already there in indexed form. Sorry, I skipped the last step, which I suppose I should say. You can also happily create syncs, sort of write the stuff back out to Kafka topics if you like. And there's a bunch of other interfaces. You can literally just log into this and type select whatever query you want. And that's a little bit of a shorthand for like go and build a materialized view and read it out. But it gives you the experience. If your tooling, for example, that's wrapped around such a system gives you the experience of a version of Postgres maybe that goes a lot faster when you materialize a view and requery from it. All right, so let me call out some of the hard stuff, and I'll tell you after the hard stuff, we'll spend like a moment or two talking through some of the really cool stuff. There's like some new good things that happen with us that aren't just us screwing things up. So it's 3 classes of things, and I'm sure there are more of them, but these are the ones that stand out the most to me. So first off, all of the queries that we write need to be Dataflow. Like the only tool that we have is Differential Dataflow. We need to turn all of the queries into actual Dataflow, and this can be pretty hard. I don't know if people are familiar with decorrelation of correlated subqueries, but this is, to my understanding, is a thing that's only recently, like the past, 5-10 years, been sorted out well enough that you can actually decorrelate arbitrary subqueries. Meaning, if you're not familiar with correlated subqueries, the scoping rules for SQL are a nightmare. You can basically reference any field in any relation from anywhere else, and it introduces an implicit join, like all the way across some big query, which is then on the person implementing the SQL system to figure out what that even means and implement it. So we actually need to turn that into Dataflow instead of just potentially bailing out in a some brute force execution. Other things like order by and limit are surprisingly non-trivial, especially in a system where you need to be able to retract records. So if you only ever added records, it'd be totally fine. But if you need to delete them, things are more awkward. And case statements are also, a conditional execution is a pain in the butt. Case statements are part of SQL where you're not supposed to execute the thing inside unless some condition is true. And that's in the Dataflow setting where you do whatever you want and you push the results forward. This is again complicated because maybe you shouldn't have even executed the thing and you might crash the system or do something really dumb. Sort of dovetailing a little with like control flow interruption generally is challenging. So a lot of these systems, parts of SQL have runtime errors, basically. Like they have things that you can express in SQL that may not have well-defined answers or may have answers that are supposed to be wrong. You're supposed to tell someone. Division by zero is like the classic example, but there's other SQL constructs that are supposed to error out if a subquery returns more than one value, for example. That's just, yeah, so getting that right is again super tricky. And like a big one, and I gotta say we haven't made a massive amount of progress on this yet, but optimization is kind of different in this setting. In particular, execution time isn't really what we're trying to optimize for anymore. Like in a traditional relational or even analytic processor, the goal is to get in and out with the query as fast as possible. That increases your throughput. That just basically gets everyone using your system out of the way. We're not really that worried about this anymore. The big thing is actually memory footprint for us. So trying to figure out how to restructure queries to maximize the sharing of state. So typically in the form of these arrangements, but also like many of the optimizations that we do are local transformations that reduce the memory footprint. And I don't want to say that memory footprint isn't important to more traditional systems, but it is promoted dramatically in importance here.
I mean, I think, I'm sorry to interrupt. I mean, I think like,
yeah,
it's not
go ahead.
Execution time isn't what you care about. It's that execution time doesn't even really seem particularly meaningful in this setting. Although we can imagine scenarios where there's like a anomaly detection system where you do have like an SLO between when the tuple that changes everything enters the system and when the alert comes out or something like that, which I guess looks like execution time of a pull-based query.
Yeah. No, you're right that, I mean, maybe a different way to say it is that in traditional systems, the goal is to sort of minimize the time from hitting enter on your select query to getting results back.
Right.
And there's a lot of stuff that goes on in that, like parsing the SQL query and optimizing it and all sorts of, there's a lot of stuff on that critical path. And we're a little bit more comfortable saying, you're probably planning on setting up a view that's going to be slightly long-lived. So if we spend a little bit more time thinking about it now, that's fine. You know, it's not the end of the world. The bigger thing is it's very binary. Like if you blow your memory budget, you lose all of the good stuff that you have. And anything that we can do to get you under that budget is worth doing because everything else goes out the window if you can't actually get effective random access to the data. But actually, there's a whole bunch more metrics too. I mean, like, yeah, latency is definitely one. Query latency, data latency, I don't know. It's a thing that we're definitely still working on shaking up. But at the moment, people using the system, memory is very much like once it works great, and they love it. And sometimes they write a join that accidentally is a cross join, and they detonate their VM, and that's sort of the problem. That's the failure mode. All right, I'm going to say just a few cute things. Actually, oh no, we're out of time. Let me announce the names of a few cute things, and then I'll stop. So there's a few neat things that happen in the stream processor type setup that just don't work in data warehousey type settings. So if you want to have unbounded streams, you totally can. And lots of the queries that you can express here work great on unbounded streams because when you specify a view, you're telling us what you care about. We don't need to record the whole data set for you. Because you've already told us, actually, no, I only need this subset of it. I need, after an aggregation, the aggregations allow us to demolish bits of data and shrink them down a lot. There's some cool stuff about memory management. So like a lot of queries work great in SQL, but they result in unbounded state. Like Windows are a good example of this over on the right. So the query is just fine. It's the behavior that you want to program. And by letting people write queries that are change streams, they can actually write corrective memory management changes. So you can write a query that changes your input to delete stuff you no longer care about, for example. And that's sort of weird in SQL, but like supernatural actually in these sorts of setups. And finally, unfortunately, I won't be able to do this justice. Lateral joins are amazing. There's a blog post on this that maybe I should just tell you to read instead. But if you're familiar with papers like Noria is this cool paper out of MIT that shows how you can do SQL queries where you sort of partially materialize state and It turns out it's really closely related to a lateral join. And if you incrementally maintain a lateral join, you're getting sort of the streaming equivalent to prepared statements. So people show up with bindings to query parameters as data, and you are sort of programmatically turning off and on the monitoring of certain change streams but through the magic of the lateral join, which is again query decorrelation stuff. That's not, it's so much more interesting than that, or is my take on it, but I'll have to defer to some other content. All right, last slide. I just wanted to make sure you had some pointers if you're interested. Materialize is sweet. It does lots of good stuff, but it gives you nice consistency all the way through, high throughput, low latency, and is just meant to be a nice solid piece of tech that everyone should eventually have access to and be able to use in their toolkit. you can check out materialize.io. That's the place where you go and you sort of the commercial stuff. But good docs, good demo, like all those things that real organization has to do should be there. We should have good explainers, blog posts explaining what's up. And the repos are all public too. You can go and check out all of the code, grab it and read through everything, see how we did stuff, ask questions, stuff like that. But I'm going to stop there. I apologize for going over time. Anyone who needs, well, sorry, I don't run this joint, but like my take is anyone who needs to bill should feel welcome to, and I'm happy to stick around and answer questions.
Great talk.
I'll ask a question in case people are using the time to think. So I'm still like stuck on the slide with the data flows where you're doing like processing from sources and building this like intermediate materialized view, and then using that sales to like derive profit later. So like it's reminding me of the Spark paper, and so I'm thinking like what happens if there's a failure? Like while you're computing, is there any checkpointing that you do so that you can resume the computation, or do you begin from the beginning?
That's a great question. One thing to point out is that fault tolerance in systems like Spark and also in systems like Materialize are essentially a performance optimization. So this is different from a database where it's required for correctness. Like you always have the ability to rerun the computation if you want. So at that point, it definitely becomes a question of what's the most efficient way to get back up to running. And there's a few takes here. We definitely have the ability to persist the input data that comes in so that we can replay it. The plan is to make sure that stays compacted and small and current. But from experience, realistically, like if you actually want low latency guarantees, you want active-active replication. You want to actually, even with something like Spark, waiting 5 minutes before it comes online and starts giving you data again. That's not good enough for most people. Or sorry, there's a class of person for whom availability is the actual goal. Fault tolerance is really about fast recovery and minimizing sort of the exposure window to additional failures. So our story is very much active with fast recovery behind, where fast recovery is more of an engineering decision than a religion, right? So we don't have particular opinions on how you should checkpoint state. If we can get it back up running as fast as possible, we'll do that a few different ways.
Hey Frank, this is super neat. One connection that I see that's sort of latent here that's interesting is just log-based replication, and of course, change data capture in industry means that you read the log from Oracle and you translate it through some horrible third-party language to load DB2 or whatever horrible thing you do. So I'm curious, as you reflect back on that legacy technology, they didn't separate the logs into query relevant changes and say structural changes like index builds or disk block allocations or whatever. Do you envision a world in which, like, I don't know, there's a standard for this or something so that change data capture doesn't become this horrible black magic?
My understanding at the moment is that it's going to be, for the foreseeable future, at least Debezium is what people are going to be using, if you're familiar with that. And it's mostly just that because everything is filthy, the people who actually went and wrote the stuff, so some folks from Red Hat, essentially, who went and wrote extractors for Postgres and MySQL and DB2 and all these things into a relatively common format. It's not perfect. Like, it's got errors and it's not consistent. Sorry, it's not consistency that's a bad word. The properties vary across the different databases from which they extract data. I don't know. It would be nice. We clearly want a different thing than other people want. Like we're very interested in the logical contents of the data, and other people are who are watching us are potentially much more interested in, what actually happened physically in the database. There's good reason to have captured that.
I don't know.
As well.
You seem to be, the right answer for the future. We're going to have auto scaling, shifting infrastructures. The whole vision of data independence from databases a long time ago is we want to capture the logical, not the physical. So it seems like, you have God and time on your side.
Yeah. Well, I think it's, I definitely support you. I think this is a good idea. I guess what I don't want to say is, like, I think we are unlikely in our day-to-day to actually put something together that would satisfy everyone. And my experience with standards and stuff like that is that typically you throw everything in and see what happens. I would say that I think there's a totally sane argument to make, just like you said, basically about if different systems want to communicate the essence of their data between each other, it's totally reasonable to think about how would you want to express that. And Andrea Latuada at ETH, this is one of the things that he was thinking about for a little while, which is like, take or leave differential data flow, whether you like it or not. Having something like its format for exchanging data between different implementations of systems is a very sane thing to want. And that maybe that's a legitimate candidate for how people should talk about how their collections have changed. But I don't think we're going to create the standard for that. I mean, we'll tell people what we did, of course, but politically that sounds exhausting. I'm already on the SQL streaming standards working group or something like that, and we had a meeting, and I basically told them that, like, oh, you don't need to do most of what you're doing. Like, just have incremental view maintenance, and I'll do most of it for you. It's a very unpopular opinion.
Frank, I had a couple questions about like related work. I guess one of them is sort of about compatibility, and one of them is about comparison. So I found myself even early on reading the differential data flow stuff, wondering how that would interact with systems like Nectar that also are built on top of timely data flow and also are all about reusing computation just in a completely different dimension. And so Aditya's question got me wondering, like, do you feel like, is it just technically more complicated? Like will, and this is really more a question about differential, I guess, than Materialize. Like, is differential, does that make it easier to do something like Nectar or harder, or are they completely orthogonal and it's just a matter of doing the engineering to support multi-query optimization and reuse previous results and so on?
I think it's mostly the engineering. I mean, I think, I don't think there's anything fascinating that we've introduced that is going to make the application of any of these techniques much harder. And in fact, if anything, we've given a bit more slack. Like, you have a bit more time to think about which queries might be appropriate. Like, one of the main pain points for multi-query optimization has been, well, how long do we wait before taking a collection of queries and trying to joint optimize them?
Mm-hmm.
So with these streaming queries, if these are up for hours at a time, and we can at any point look at the collection of queries that are currently there and consider re-optimizing them, we have the ability. I mean, maybe it changes the definition or the trade-offs a little bit. That, like, multi-query optimization could be a bit more about over time identifying commonalities, but not having to urgently do it quite so quickly. Nectar, I think, applies just directly. Like, in my recollection was Nectar was sort of dead simple. Just like look for exact matches of
it's like name the AST, hash the name of the AST. It was pretty straightforward. Yeah. So my other question was about, I'm glad you brought up Noria, because I have these notes that were like, what is this malarkey in the abstract about how microservices or how people do differential or do incrementalized computation now? Why aren't you comparing against a system like Noria? It sounds like you are.
Yeah, I can definitely talk you through the comparison to Noria. I think the right take there is that the Noria folks were looking at a very specific vertical that was a certain class of web applications that could tolerate eventual consistency, for example. So that Noria's consistency guarantees are only, it's like eventual consistency plus a little bit. Like, there's a little bit more that it gives you, but doesn't land cleanly in existing buckets. No iteration, that's just not a goal for them. And a few slightly, I mean, there's some exciting performance question marks that I have questions about. They do these, where we do push-based computations, they do these upcalls that have some interesting properties about how much they grow as they go back up a data flow. And I imagine if you ask John, he has a complementary set of, like, well, obviously timely data flow is a disaster for the following reasons. But I think that the main one is this connection with the lateral joins, that, like, the sort of signature, one of the signature features of Noria was the ability to take bindings to these sort of queries and reuse the same data flow with multiple bindings, which my take is, I think it's an idiom now in Materialize. If once you've worked out all of the, here's how to decorrelate a query, here's how to turn that into an actual data flow graph without having to do it by hand. But yeah, there's an evaluation in the Noria paper comparing with differential data flow, and we were able to express the same computations, and the scaling properties were definitely in Noria's favor, which was assessed as like eventual consistency gives you some wins over strong consistency.
Sure. Thank you.
Oh, Frank, I have a couple questions. Really love the presentation. You mentioned a couple of times that you're doing a lot of optimizations around memory, and I can see how there's low-hanging fruit there and so forth. But I'm curious, what are the performance requirements that you have for these, seems like potentially very large amounts of memory that you would be using? And are there technologies other than DRAM that might suit the need there?
That's a good question. I mean, at the moment, we're literally just looking at DRAM. This is mostly a, what's the right way to say this? Like an operational consideration. The people who are showing up aren't necessarily, sorry, this isn't a dig at them, but aren't necessarily the most sophisticated folks. They're not looking at NVRAM or anything like that. They're literally just like, hi, I'd like to check out some, bog standard VMs from AWS. Can you help me?
I see. But if you say even put SSD in there, would that help?
Yeah, it does a little bit. There's some
curious.
work. Oh, sorry. Yep.
Yeah.
Like all of this spills out to swap in principle just fine, though in practice there's some hiccups. Internally in differential data flow, a lot of work is done to make sure that access to state is through sequential passes, or it's not random access, but things that devolve to sequential access. So if it did spill out onto swap, performance would degenerate to look more like your sequential access to swap to SSD rather than your random access to SSD.
Okay, got it. And one follow on to that. So I think a lot about serverless, and one thing that is kind of missing from serverless today, and we sometimes think about should it be added, is essentially serverless memory. So I'm curious about the kind of duty cycle, or whether you would benefit from sort of brief bursts of memory, or whether it's really kind of a steady state requirement.
Yeah, it's a good question. I mean, elasticity comes up a bunch. People are like, well, first of all, people want elasticity, period, because all the other systems have it. They don't actually say what they want it for. But my experience has been, so first of all, like it doesn't do anything particularly good for us, as far as I'm aware. We don't generally have big bursts unless there's also a big burst of data and compute and all these things. That being said, a lot of what goes on in these things is usually some fairly compute intensive filtering and data transformations at the moment of ingestion. So there's a lot of opportunity for elasticity there in these sort of stateless operators. Ones that are parsing JSON or something like that is a pretty expensive moment for us. But I'm not sure, like memory doesn't seem to come and go quite as much for us. We do churn through it, but not in spiky ways.
Thanks.
Hey Frank, I had a question about the sort of mixing of the SQL workflow with maybe other like UDFs and other sort of piece of computation that might fit in. Are those the kinds of things that would also need to be expressed within the differential data flow? Are there certain guarantees or constraints sort of integrating these other types of computation into the what gets built up through the SQL queries?
Yeah, it's a good question. So there's at least two takes on this. One of them is like a standard pressure release valve is you can always sort of round trip things through Kafka if you need to. Like in the worst case, write stuff out there, have a K-streams job, grind through it using an additional tool that you have in your ecosystem that you would normally use if you were building up your own streaming data flow. I think our plan is, Rust has relatively, this is all in Rust, I guess I mentioned that, but Rust has relatively nice support for WebAssembly. And one of the takes is that if you have source access to the stuff that you'd like to run as UDFs, presenting as WebAssembly, we're happy to compile it for you and then link it in because of the nice properties that that has about security and what have you, and not terrible performance properties. I mean, I think we're much less technologically advanced than a lot of other databases are surrounding this. Certainly, than something like Hyper or LegoDB or something like that.
Cool, thanks. I guess another question I sort of had thinking through this was, what are the sort of ramifications for like a time series data? I guess sort of use case where there's sort of historical data that you might want to do these windowing operations over. Does that, are you able to make any sort of simplifications or performance guarantees, or does that sort of stretch the system in the wrong way?
Yeah, so it's a good question. Actually, differential dataflow works as a time series dataflow processor in a sort of interesting way, in a way that a lot of time series databases don't, which is that if you maintain full historical detail, and you don't have to compact the data, then its logic actually will map your non-trivial computation over the full history. So rather than just pulling out sort of key value, like for each key, give me a series of the measurements at a particular time, it is a functional way to map computation across those things. That being said, like the internal representation of data is sliced by key rather than by time. So most time series databases, or like timescale or something like that, will organize their data so that you can efficiently subset by time and get the most recent sets of measurements much faster than get all of the measurements for a key. So it's definitely not going to do nearly as well at this sort of core time series task of random access to time series. But it does actually do surprisingly well if you needed to take a bunch of these and do as of joins across them. I mean, there's some systems like KDB and ClickHouse will do these sorts of things for you, but like as far as I understand, timescale